Okay, so we've covered the whole numbers and all that stuff. Next step is to take a look at some of the other forms of numbers. So the next form we're going to look at is our fractions. And we've looked at them a little bit in the first hour, taking something like 3/4 and defining that numerator, the 3, is a count. It's telling us how many. So here we have 3 of something. Well, that's pretty easy to grasp. But the 4, the denominator, is a name. And that's the label of what we have. Like having 3 cows or 3 inches, we have 3/4. So the next step is to define what it means to be a fourth. The easiest way to do that is to go back to the old elementary school drawing. Pretend that looks like a circle of a pie or a pizza or whatever. And the fourth means that that one whole object gets cut into 4 equal pieces. Pretend those look equal. When I do drawing, you guys are going to have to do a lot of pretending, just so you know. Anyway, one whole object gets cut into 4 equal pieces. Or the other way of looking at it is, it takes 4 of those pieces to make a whole object. We have 3 of them, so it would look something like this. I don't color real well either, as you can tell. One of the first things we need to do with fractions, as we saw in last hour, we run into fractions with different names, and we need to rename them, or give them what we call a common denominator. One of the simplest ways we can rename them in this drawing would be to just cut these into equal slices. Let's say that each piece gets cut into 3 equal pieces like this. Pretend those are equal also. Now, how many pieces does it take to make a whole object? Well, if we were to count them, 1, 2, 3, I'll let you guys count. 12, right? We had 4 to make a whole object. Each of them got cut into 3 pieces, so 4 times 3 is 12. How many pieces do we have now? 9. Yeah, we had, oops, I don't have 9 here. There. We had 3, and each of them got cut into 3 equal pieces, so 3 times 3 is 9. So we now have 9 twelfths. That's what this picture shows. Do we have any more or less than we did before? No, we have exactly the same amount. So 9 twelfths and 3/4 are exactly the same amount. They just look different. And that's what the whole process of renaming a fraction is we're trying to keep the same amount and just change the appearance. The reason for that was this thing right here. What we multiplied by was 3/3. This 3 tells us it takes 3 pieces to make a whole object. This 3 tells us we have 3 of them. In other words, we have one whole object. Whenever we multiply by something that equals 1, what does it do? Absolutely nothing. Right? It does not change the value. It keeps the value the same. But we can use it to change the appearance. When we look at doing measurement conversions in our next unit, we use that same idea of a fraction that's equal to 1, called a unity fraction, by multiplying by a fraction that's equal to 1. We can change the appearance without changing the value. So let's say I have 2/5, and I need to change its name. Well, the first thing we need to know is what we want to change the name to. So let's say I want to change this to 30/5. Well, just like up here, when I had to cut those 4 slices into equal pieces, same thing down here. The only question is, how many pieces do I need to cut each of those 5 slices into to get 35? 7. So 5 times 7 equals 35. Now, if I cut those into 7 pieces, the ones I already have also get cut into 7 pieces each. 2 times 7 is 14. So 14/35 is exactly the same value as 2/5. It just has a different appearance. Or we might have 1/3, and I want to change that into 12ths. What am I going to get here? 4, good. 3 times 4 makes 12, so 1 times 4 to get 4. We can go the other direction. We can run into something like 48/64. If you try to visualize taking 64 pieces to make one whole object and having 48 of them, that's kind of tough to visualize. Actually, the human brain on average can visualize between 8 and 13 things before things start to fade. But we can simplify this. If we'd gone up here if we'd taken this 4/12 that we got, we could have reversed that process. We multiplied by 4 to get from 1/3 to 4/12. If we were to divide by 4 on top and bottom, it would take us back to 1/3, right? We can reverse this process. Well, up here, we saw that it had been multiplied by 4. Down here, we don't have that. We have to be able to look at those two numbers, the 48 and 64, and figure out what both of them can be divided by. What's one number that can divide into both of them? 8 will go. Good. 48 divided by 8 is 6. 64 divided by 8 is 8. Are we done? No. What can we still divide out? Both of those can still be divided by 2. Is 3/4. Now, many of us were always taught that you have to find the largest number that goes into both of those. It's not true. I mean, it's easier if you do. If you had looked at this and saw both of those can be divided by 16, it would have reduced it in one step. We would have got 3/4. But you don't have to see that. In fact, a lot of times it's easiest if you just see any number that divides into both of them and start doing it. And as the numbers get smaller, it's easier to see what else can divide into it. Like here, you may look at that and at first all you see that they're both even, which means they both can be divided by 2. You get 24/32, and from there it might be easier to see what else you can divide by. In fact, you could just keep dividing by 2 if that's all you see. They're both even, so they divide by 2. And eventually we still get down, as long as we do everything accurately, to 3/4. It's just a little bit more work and time to do it this way, but we still get there. So that's the trick, is looking at those numbers and seeing what both of them can be divided by. So here, what can both of those be divided by? 5, good. Giving us 7/8. How about this one? What can both of those be divided by? 6, giving us 5/7. What do you think? Not so bad? Well, we can also run into something that looks like this. Now that's, obviously we see that the top number is bigger than the bottom number. The 7, of course, tells us it takes 7 pieces to make a whole object. The 44 says we have 44 of those pieces. We have enough pieces to make a whole object. In fact, we have enough pieces to make several whole objects. How many objects? Well, how would we figure that out? Okay, so 44 divided by 7. If you punch that in your calculator, it spit out something like 6.285711429 approximately. What's that tell us? Other than I have way too much time on my hands. Well, it tells us we can get 6 whole objects out of it. The fact that there's a decimal tells us there's something left over. Be careful not to read anything else into that decimal other than that. How do we figure out how many pieces are left over? We still have some of those 7ths left over. Well, how many pieces did the 6 whole objects take? Yeah, 42. 6 objects times 7 pieces each was 42. How many are left from the 44 we started with? 2. 6 and 2/7. Basically what this is a division and a remainder. Let's say I have 38/5. What I'm doing basically is doing a long division. 5 goes into 38 7 times. 7 times 5 is 35. There are 3 left over. So what that is saying is I have 7 whole objects and I have 3 pieces, or 3 of those fifths left over. Now with 38/5, many of you could probably do that in your head, but you might run into something like this, where you can't do it in your head. So let's look at that. $11 goes into 15 once. There's 4 left over. Bring down the 9. 11 goes into 49. 4 times, that's 44, with 5 left over. Make sense? This right here is what we call an improper fraction. Now the word improper implies that there's something wrong with it. There really is nothing wrong with it at all. In fact, there are times that we prefer it in that form. It's just called improper because we don't like having the numerator bigger than the denominator. This is what we call a mixed number. It's a mixed number because it mixes whole numbers with fractions. There are times, as I said, where we prefer the improper fraction. So we need to be able to take something like a 6 2/3 and convert it back into an improper fraction. To do that, we need to break this 6 whole objects back into pieces. How do we know how many pieces to break each of them into? We look at our name, our denominator. This tells us that each of them has to be broken into 3 pieces. So 6 times 3 is 18. We had these other 2 pieces before, so it is now 20 thirds. Oops, I don't know where the extra 0 came from. No charge for the extra 0. 7 4/5. So again, we break the 7 into pieces, so 7 times 5 is 35, and plus the 4, 39/5. Simple enough? Okay. Well then, let's get back to operations with numbers. We saw 1/3 plus 2/5 as an earlier example. We said we couldn't add them because they have different names or different denominators. So our next step, we've seen how to rename them. But before we can rename them, we have to figure out what name to turn them into. What's that common name going to be? Well, there's a couple of ways to go about it. Some of you can just look at it and you figure out it's 15. If you can't figure that out, you look at it, you can make lists. I would start with the 5 because that's an easy one. 5, 10, 15, 20. In fact, I don't even have to really write that down. I just know it's going to be the 5s and the 0s, right? 3, well, 3, 6, 9, 12, 15, there's our match. Another possibility is you can always just multiply them together. 3 times 5 is 15. That won't always give you the smallest one. We've always been taught you need that least common denominator, which again is kind of a lie. Any common denominator will work. It's just the least common denominator is the one that's the least amount of work. So we got 15 as our common denominator. Now we need to go about renaming our fractions. What do we do to a 3 to turn it into a 15? Times 5. So we have to multiply the 1 by 5. What do we do to the 5 to turn into a 15? Times 3. So multiply the 2 times 3. And now when we add, just like always, we combine the counts. 5 plus 6 is 11. And we keep the same name. Now, I'm not going to spend any more time on just simple fractions. We're going to jump up to mixed numbers because it's just more complicated that way, I guess. We're going to look at something like 5 1/2 plus 3 2/5. What's my common denominator going to be between 1/2 and 2/5? 10. Now, I always rewrite the whole number. Some places, some books just have you rewrite the fraction, but if I just rewrite the fraction, the whole number and the fraction are too far apart and I forget about the whole number. Anyway, 10 is going to be our common denominator. What's this going to become? 5 4. 5 and 4 make 9/10. 5 and 3 make 8. 8 and 9/10. Now, not all of them are that simple. We run into ones like this. So we go to line this one up. Again, I rewrite the whole number. What's my common denominator? 12. Good. What's this going to become? 10 and 9. Now we go to add. 10/12 plus 9/12 is 19/12. What's wrong with that? Not necessarily wrong, but what do we have to deal with? That's improper. We can break that down into how many whole objects? 1 with how many pieces left over? 7/12. Now, just like with whole numbers, we're going to keep part of this and carry it. You can see I put the fractions here, just like it's the last digit of the number. And that's really what it is. It's the last digit of the number. So we're going to keep the fraction part in the fraction digit, and we're going to carry the 1. 1 and 7 makes 8, plus 4 is 12. 12 and 7, 12. Here's one, by the way, that if we had done 6 times 4, we would have got 24 as our common denominator. That still would work. That would just give us 38 24ths, or 1 and 14 24ths, which can be reduced to 7 12ths. So if you just multiply them together, the worst that can happen is you have to reduce it at the end. It just gives you a little extra work is all. Let's subtract. So if we go to subtract something like this, common denominator, 8. Sometimes one of the denominators is the common denominator. So that means this one's just going to stay 5/8. What's this one become? 6. And just like with addition of fractions of mixed numbers, and just like addition and subtraction of any form of number, like our whole numbers, we're going to start on the right, work our way back to the left. 6 minus 5 is 1/8. 8 minus 2 is 6. Now, once again, it doesn't stay that simple. You might be learning at this point that I always make it worse. We have 9 and 1/4 minus 5 and, oh, what I'll go 5 6. What's my common denominator? 12. What's this going to be? 3 and 10. We go to subtract here. 3 12ths minus 10 12ths. We got an issue, don't we? Just like with whole numbers, in any form of number, I'm going to borrow from the next digit. I can borrow from the 9 and make it an 8. But what I borrowed was 1. And remember, fractions are all about the pieces. How many pieces are in that one thing I borrowed? My denominator is 12. That's how many pieces. So I had 3 plus 12 gives me 15 12ths. Now it's 15 minus 10 is 5 12ths. 8 minus 5 is 3. Let's try 7 and 3/8 minus 2 and 4/5. So again, common denominator, say 40. 40, there we go. What's this going to be? 15 and 32, good. 15 40ths minus 32 40ths? Can't be done, right? What do we have to do? Borrow. This is going to become 6, and what do we do here? Yeah, we have to add 40. Now there's 40 pieces in the one object we borrow. So there's 55 40ths. 55 minus 32? 23 40ths. 6 minus 2 is 4. Any questions on subtraction? Okay. Multiplication. We might run into something like 1/4 times 2/5. When we multiply, as we saw in the first hour, we just combine counts and also combine the names. And in fractions, that means we just multiply straight across. 1 times 2 is 2. 4 times 5 is 20. And of course, you might see that that can be reduced by 2 to give me 1/10. Now, some of you might be thinking, why didn't you cross cancel? And I could have here. If we look at this, we realize this is going to be 1 times 2 over 4 times 5. And you might see that the 4 and the 2 can both be divided by 2 and reduced. Because that's going to just come out in the multiplication anyway, we can reduce before we multiply. We could have come up here and said, hey, we're going to divide the 4 by 2 to get 2 and the 2 by 2 to get 1. And now it's just 1 times 1 is 1, 2 times 5 is 10. We have 1/10. And we got our answer already simplified. Now, in a problem like this, it's about the same amount of work either way. But we can run into problems like this one. 24 25ths times 35 36. What can I cross cancel there? 25 and 35 can both be divided by 5. This will give me 5 and 7. What else? 24 and 36 can both be divided by 12. Gives me 2 and 3. So 2 times 7 is 14. 5 times 3 is 15. 14 15ths. I mean, we could have gone ahead and multiplied out. 24 times 35 is 840. 25 times 36 is 900. And we could have gone ahead and reduced those. We could see that those can both be divided by 60. But that more work than we want. It's easier to reduce it before we divide or before we multiply. Now, just like with the addition and subtraction, I'm not going to waste a lot of time on simple fractions. We're going to go to mixed numbers. We're going to look at something like 7 1/3 times 5 and 3/4. Multiplying mixed numbers is actually a very, very long and difficult process. In fact, if we were to go to any university and find 10 math majors, I'd be shocked if even one of them could show you the proper way to multiply mixed numbers. So how do we do it without making mistakes? What do we do to get around it? Well, we turn them into improper fractions. 7 1/3 becomes what as an improper fraction? 22/3. Good. 5 3/4 becomes 23/4. Now, just like any other fraction at this point, we are multiplying, so we can cross cancel. 22 and 4 can both be divided by 2 to give me 11 and 2. And now we multiply across. 11 times 23 is 253. 3 times 2 is 6. And to reduce that, again, it's just a division and remainder. 6 goes into 25 4 times. That's 24 with 1 left over. Bring down the 3. 6 into 13 twice. That's 12 with 1 left over. So 42 and 1/6. Not so bad? Let's do one more example quick before we move on. Anybody want to see how to do that with the mixed numbers, by the way, just for the heck of it? Anybody, a couple of you are curious? Okay, why not? It'll only hurt for a little while. 5 3/4. Well, just like if we had like 37 times 48, you have to take the 8 times the 7, but also the 8 times the 3. Well, same thing here. You have to do the 3/4 times the 1/3, but you also have to do the 3/4 times the 7. So we've got 3/4 times 1/3 gives us 3/12, or 1/4. All right, 3/4 times 7. How do we multiply a fraction times a whole number? Put it over 1. Right? 7 over 1 is now a fraction. 3 times 7 is 21. 4 times 1 is 4. That is 5 and 1/4. Now we move over to the 5. We have 5 times 1/3. We're going to make 5 over 1 times 1/3 is 5/3. 1 2/3. Oops. Put it over there. Then 5 times 7 is just 35. Now we have to combine these over here. We have to have a common denominator, which looks like it's going to be 12. So this is 3/12, 3/12, 8/12. So 5, 1, and 35. 3 and 3 is 6, plus 8 is 14/12, or 1 and 2/12, or 1 and 1/6. We're going to keep the 1/6. Carry the 1. 1 and 5 is 6, plus 1 is 7. Plus 5 is 12. Carry the 1. Oops, what did I do wrong there? I'm off by 1. So, no, I'm not. 42 and 1/6. I am right. Okay. Some weeks by this point in the week, the little hamster has climbed off the wheel for the weekend already. So for we get the same answer. Now, I don't know about you, but I don't really like that process. I'll stick with the improper fractions. Let's do one more example of that before we move on. Tell me what to do. Five times 7 is 35. So 36/5. So 3 times 5 is 15, plus 2 is 17/3. And then not everybody at once. Plenty of time for everyone to help out. Perfect. 36 and 3 can cross cancel by 12 or by 3 to give me 1 and 12. And then multiply. 12 and 17, 204. 5 and 1 is 5. So if we divide that out, 5 goes into 24 times. 0 left over, bring down the 4. Got to be careful, we need a 0 there because we didn't do anything with the 4. So it's 40 and 4/5. Good stuff? Great stuff? Any questions? Okay. Division. We said that division follows the same rules as multiplication. When we multiply fractions, we just multiply straight across. Does that mean I can divide fractions by dividing straight across? Can I do 12 divided by 4 is 3, and 25 divided by 5 is 5? Does that work? Is that the right answer? Actually, it is. Does it work every time? Sure does. Why don't we do it that way? Because we're mean math teachers and want to make it more difficult? That's only part of it. Because we run into things like this. 3 divided by 2 doesn't work out so neatly, does it? And 4 divided by 3 is worse. What have we been taught to do to solve a problem like this? Yeah, change the division into multiplication by a reciprocal. Instead of dividing by 2/3, we multiply by 3/2. 3 times 3 is 9. 4 times 2 is 8. 1 and 1/8. Where did this process come from? Why do we multiply by a reciprocal? Well, you just remember, yeah. Well, it's one of the many things that we're just told how and never why. Just do it. That's how it's done. Just do it, right? As you can tell, I might have some issues with some things. The original process of dividing fractions, again, just like the long division with whole numbers, it's been shortened and changed. We've come up with shortcuts to make it easier to the point where we don't even recognize the process anymore. What they did is they said we're dividing by 2/3. To make sure that we can divide by 2/3, we're going to take the 2 and the 3 and multiply them together. 2 times 3 is 6. We're going to use that 6 to rename our fraction up here. So we're going to rename the 3/4 by multiplying by 6 on top and bottom. 3 times 6 is 18. 4 times 6 is 24. Now if we divide, 18 divided by 2 is 9. 24 divided by 3 is 8. 9/8 or 1 and 1/8. So the big question is, how did we get from this to just multiplying by a reciprocal? And it's not as big of a leap as you might think. At some point, somebody looked at this and realized, hey, if I do this part first, it's violating a couple of rules, but it works. If I do this part first, taking that 6/6 divided by 2/3, I will always get this same fraction flipped over. So they named it a reciprocal. And then all that's left to do is multiply the first number by that reciprocal. So that multiplying by a reciprocal is explained by the longer real process. It's just we shortened it to the point of not being able to see where it came from. But there is a good reason for it. It's not just like I was told in high school, because anytime you multiply by a reciprocal, it's the same as dividing. Okay. Now, of course, division, since we're going to turn it into multiplication, Makes sense that we're going to do the same things we did with multiplying mixed numbers. We're going to turn them into improper fractions. So 5 3/4 becomes, oops, don't know where that came from, 20 3/4, good. 2 1/3, 7/3, right? Is this multiplication now? No, it's still division. How do we change it into multiplication? Reciprocal. We're dividing by 7/3, we're going to multiply by 3/7. 20 3/4 doesn't change. Now, since this is multiplication now, at this point, if there was something that would cross-cancel, we could do that. Unfortunately, at this point, there's nothing that cross-cancels. 23 times 3 is 69. 4 times 7 is 28, which gives us 2 13/28. Not so bad? Okay. Well, a couple other things we need to show you. Oops, stop that. Anyway, we've looked at the counts and how the counts affect operations, the whole numbers, and even with fractions. It's time we look, or not the counts, the names, how the names affect things. It's time we look at the counts a little closer. What does it mean to have a count of 6 or a value of 6? And it goes back to, it goes back to this basic idea of a number line again. It is not my day for technology, apparently. What the 6 stands for is something we call a vector. And a vector is just a really fancy word for an arrow. The vector for 6 starts at 0 and it goes to 6. That's it. The process of addition, for example, 6 plus 4, is defined to take the vector for 6, take the vector for 4, and put them together. You can see that goes to 10, so 6 plus 4 is 10. That's all the mechanical process of addition is combining vectors. Well, with that definition in mind, we can take something like 6 plus a -2, and it still makes sense. Here's our vector for -2. Put that with the 6, and we end up with 4. Now, I'm not expecting you to draw out number lines every time we add with these negative numbers. The positive and negatives mixed together, by the way, are called integers. But I do keep that picture in the back of my mind when I'm working with these. If I have 7 plus a -12, here's what I'm looking at. I got 0, 7 goes to the positive direction. The 12 is negative, so it goes the opposite direction. 12 is bigger than 7, so it's longer. So it looks like that. I didn't have to draw anything to scale or anything like that. All I did was had the directions and which one's longer or shorter. And what this tells me about my answer is, first of all, I'm on the negative side of 0, so my answer is negative. Second, it tells me the vectors went in opposite directions, so the size of my answer is the difference between these sizes. What's the difference between 7 and 12? 5, so -5. I might have -8 plus 3. So again, here's 0. -8 goes this way. Positive 3 is the opposite direction, longer or shorter? Shorter. So that tells me that I stay on the negative side. The answer is the amount is the difference between 8 and 3, which is again 5. How about this one? Here's 0, and -11 goes this way. 27, same or opposite direction? Opposite, longer or shorter? Longer. So that tells me I've made it to the positive side of 0. Again, the arrows are in opposite directions, so it's the difference between 11 and 27, which is 16. For this one, here's 0, and -8 goes this way, -14, same or opposite? Same. So this one's obviously negative. They point in the same direction, which means the values are added together. 8 plus 14 is 22. -22. Make sense? Good. Because the process of addition is important. It's vital that you understand that to have an understanding of subtraction. Let's look at something like 8 minus 3. If I were to try to draw a picture of 8 minus 3, I'd probably draw it like this. Eight minus 3 equals 5. We all know that. If I look at that picture, though, it looks suspiciously like the picture for 8 plus a negative 3. In fact, it's exactly the same picture because they're exactly the same problem. We hinted before at subtraction not being its own operation. It's part of addition, or the reverse of addition. This symbol that we know as the subtraction symbol always pairs with the number that comes after it. And what it means is add the opposite. So when we're saying 8 subtract 3, what that really means is 8 add the opposite of 3. So if I have 9 plus, I have 9 minus 12. What it really means is 9 plus the opposite of 12 is negative 12. So now I have positive 9, negative 12. This is going to be negative 3. I have negative 7 minus 4. That's going to become negative 7 plus negative 4. 0, negative 7, negative 4. That's going to be negative 11. I have an 8 minus a negative 3. That's going to become 8 plus, what's the opposite of negative 3? Positive 3. 8 plus 3 is just 11. Or I might have negative 12 minus a negative 8. That's going to become negative 12 plus the opposite of negative 8 is positive 8. Negative 12, positive 8, we're at a negative 4. What do you think? Still better than a sharp stick in the eye? Okay. We'll work on it. We've already mentioned that multiplication is repeated addition. 5 times 3 is just 5 plus 5 plus 5. Give us 15. With that definition out there, it's fairly simple to comprehend negative 5 times 3. That's just negative 5 plus negative 5 plus negative 5. Or negative 15. Negative 5 added together 3 times. It's a little bit trickier to comprehend 5 times negative 3. That's saying take 5 and add it together negative 3 times. We really can't do that, can we? But what we can do is we can switch it around and say, okay, well, let's do negative 3 times 5. So that's telling us take the negative 3 and add it together 5 times. Which gives us negative 15. The moral of the story so far seems to be that 15 is going to be involved somewhere. We're multiplying the numbers. The 3 times 5, whether they're positive or negative, is always going to give us some form of a 15. Here's the stumper, though. Negative 5 times a negative 3. Now, we've always been taught that that has to equal what? Positive 15. And negative times a negative is positive. But if we look at our definition of multiplication, this makes no sense. We cannot take 5 and add it to itself negative 3 times. Or negative 5. We cannot take a negative 3 and add it to itself negative 5 times. It doesn't work. Our definition of multiplication breaks down here. It does not work. This happens actually quite a bit in math, where our basic definition doesn't work for a particular example. So what we do to figure out how to do it is we look for a pattern, and we define the answer to that pattern to be, or to that problem to be whatever makes our pattern work. So we've already established that negative 5 times 3 is a negative 15. So let's keep going with it. Negative 5 times 2 is negative 10. Negative 5 times 1 is negative 5. Well, let's look for our pattern. So I'm starting with negative 5. If this number gets reduced by 1, what happens to my answer here? It's increased by 5. We go from negative 15 up to negative 10. From negative 10 up to negative 5. Let's go with the next number. What's this have to be to make our pattern continue? 0. Subtracting 1, we go to 0. What's this have to be? 0. Is that right? Yeah, it is. So we're going to assume our pattern works. So let's keep it going. Subtracting 1 now would be negative 1. Adding 5 would be a positive 5. Negative 5 times negative 1 is a positive 5. Negative 5 times negative 2 would have to be a positive 10. Negative 5 times negative 3 has to be a positive 15. This is only true because it makes the pattern work. So when you multiply two negatives, you get a positive, only because it fits the pattern. So if I have 7 times a negative 6, what do I get? Negative 42. Positive times a negative is a negative. Negative 8 times a negative 4, what do I get? A positive 32. A negative times a negative is a positive. Negative 9 times 5, negative 45. Good. Basically, when we multiply, if both of the numbers are positive, our answer is positive. We've known that for quite a while. If both of the numbers are negative, our answer is positive. Whereas if they're both the same, we have a positive answer. If the first one's positive and the second one's negative, of course the answer is negative. And the other way around. First one's negative, second one's positive, the answer is negative. If there's one positive and one negative, no matter what the order is, the answer is negative. For division, well, if we look at the definition of division, 16 divided by 8, of course, equals 2. But that is defined by the statement that 2 times 8 equals 16. We have to work it backwards. So using that definition of division, if I have a negative 24 divided by 6, to find out what that has to equal, we're asking what times 6 equals a negative 24. Well, since this is negative and this is positive, this one has to be negative. A negative times a positive to get a negative. And of course, what times 4 is 24? Or what times 6, sorry, is 24 is 4. So that has to be a negative 4. You can see 24 divided by 6 would be a 4, and it's negative because of the signs. 36 divided by a negative 3. Now again, that's asking what times a negative 3 equals a positive 36. Well, if this is positive, these both have to be negative. So our answer here has to be negative. What's 36 divided by 3? 12. So you can see here, with our division, a negative divided by a positive or a positive divided by a negative. Once again, if there's one of each, the answer is negative. Let's look at what happens if we have a negative 45 divided by a negative 15. Well, that's saying what times a negative 15 equals a negative 45. Well, if this is negative, that means we have to have one positive and one negative. This one's already negative, so this one has to be positive. What's 45 divided by 15? 3. Answer is a positive 3. So a negative divided by another negative is positive. So it's the same rules for division as it was for multiplication. If there's one of each sign, the answer is negative. If they're both negative or both positive, the answer is positive. Okay, we didn't necessarily get through everything for week 1, but if you're looking at the assignment sheet on Blackboard, if you can pull it up, I'll let you know the pages. It's pages 7 through 8, pages 18 through 21. We didn't talk about decimals, but I'm going to assume you guys are okay with decimals since the calculator can do those for you. But we will talk about them a little bit next week if we get some time. But the decimals are on page 29 through 32. And we did not get to order of operations. So page 23 you can hold off on for now. We'll talk about that at the beginning of next week. Homework, remember, is not collected, is not graded. I would suggest you just do the odd numbered problems. I will have the solutions for the odd numbered problems posted out on Blackboard. Check your own homework. Make sure you're doing it right. Like I said, that's where we'll start out next week, is answering any questions on that homework if you need it. If you're doing the first couple and they seem incredibly easy, don't be afraid to skip ahead and go to some of the more difficult ones. I don't want you to sit there and do a lot of busy work. Okay, with that, you guys have a great weekend.